So let's get started. Good evening, everyone, and welcome again to another session from Process Automation and Control Optimization Week by ISA Oman section. This is part of Ethraa knowledge sharing sessions. Tonight is not just another night because I have replaced my headphones, so they will never fall again during the show. And also because we are hosting an experienced engineer, engineer Khalid Al Aamri, to talk about advanced process optimization using APC and RTO. APC uh, is a short term for advanced process control, and RTO is real-time optimization. Real-time optimization. Uh, Welcome everyone, whether you are an ISA Oman member or from other sections of ISA sections. You are an engineer, automation professional, or a student, or someone who is interested to know about the future of automation. To make this short and for our new joiners, just to give you a hint about International Society of Automation, ISA in short. We are an international uh, society that consists from automation professionals, and we have multiple divisions, more than 16 divisions, whether they are in aerospace, analysis, automation, education, safety, and so on, with a 2,900 member per division. ISA shines in different countries through the professional sections, where 103 sections in 33 countries and 14 global districts, and more than 200 student chapters. Here in Oman, we have ISA Oman section that was established in 2016, and since then, the society kept growing. Today, we have more than 140 members from different companies, entities, and universities. So you might spot your company or university here. You are lucky if you found it. And if you didn't find it, don't worry, because the space wasn't enough to have all of them. We need to become a member because we offer a lot of member benefits. ISA Ethraa, which means, by the way, enrichment, is one of the benefits that you will get, which have been started long back. We have hosted multiple online sessions, webinars, in different topics, whether in OT, in IT cybersecurity, in automation, process control, and also students are sharing their final year project. Uh, Going on with the membership benefits, you will be having an access to ISA Publication Hub, where you can find conferences, magazines, books, standards, and podcast free to view for you. You will be also having direct access to ISA standards, whether in cybersecurity, in process, in automation, control valves, or functional safety. So don't wait, scan this QR code and connect with us. Grow and explore opportunities. Learn with our resources, from our webinars, and from our uh, engagement sessions. Do you want to know more about us? Here you will find us. Those are our social media accounts where we share our updates, where we share our achievements, and where we spotlight our members. So become a member today. That's my advice to you. If you scan this QR code, you will be taken to a guide on how to become a member in ISA Oman section. Without further ado, we are moving straight forward to the PACO week, Process Automation and Control Optimization Week, where we have hosted yesterday Engineer Umar Al-Bahdour from OQ-Based Industries, and today we are honored to host Engineer Khalid Al Aamri from Oman LNG, and tomorrow we will be hosting Engineer Abdullah Al from Petroleum Development Oman. Uh, Engineer Khalid Al Aamri, he is an electrical and electronics engineering, or he have done his electrical and electronics engineering studies in Germany, and bringing more than 11 years of experience in base layer protection control, advanced process control, procedural automation, and real-time optimization, plus AI applications in process optimization. Also, he is experienced in automation project management. His experience shines more in oil and gas environment, and he is skilled in applying engineering solutions to improve efficiency, reliability, and operational excellence. He is an active contributor to a technical knowledge sharing and professional development initiative. He will be taking us today through an amazing webinar titled Advanced Process Optimization using advanced process control and real-time optimization. Engineer Khalid, welcome to the show, and the floor is yours.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you very much, Yusuf. Thank you for
Always a
the
pleasure.
kind introduction as well. And thanks to ISA Oman for hosting the session. Yeah, advanced process control. Let me share my screen.
No worries. And until you share your screen, Engineer Khalid, I would really encourage our audience to take the best out of it. And if you have a question, you will be muted until the presentation ends. If you have a question, you can type it in the chat, or you will be allowed to unmute yourself once the presentation ends.
Yes, I hope I'm audible and the screen is also clear.
Loud and clear.
Alhamdulillah.
So, before we start, there's a question, engineer, how to say advanced process control in German.
Inshallah, you will hear some German words during the presentation.
Excited?
Because most of this stuff I learned, or I heard in German. I mean, the terminology, at least I used to know them in German, not in English, but then I had to learn them in English. Anyway, I see gurus here, experts, also advanced process control experts. I'm happy to see all of you, everyone here. And some of you are people I really learned a lot from. I will not mention names. Happy to see you all. Yeah, it might be very boring for some of you because you know this. It will be very, very basic. I'll try to answer the questions of why. So why advanced process control, and what it is and what it is not, and also then how to do this stuff. But really very, very basic. And then I'll touch base on RTO, and again trying to answer the same questions: why and what and how. It will be more on advanced process control and less on RTO. The aim is to connect the practical plant reliability with advanced process control and optimization concepts. So Yes. So let me start with this question. If the plant is stable, does that mean it is optimal? I will be asking you questions, by the way, during the presentation. Not many. One of them I will ask for answers. I know you will be asking me at the end of the presentation, so I'll do that before you. تغدى قبل أن يتعشى. So in many cases, the answer is no. It is not. It's not necessarily optimal if it is stable, as stability is not the final objective. A plant can be stable indeed, safe, and still not operating at the best economic point. So Engineer Omar yesterday talked about the basic control. I'll have to talk about it a bit. And he even mentioned advanced process control. I was afraid he will talk about it and they will have nothing left to talk about. So really the journey from process basic control to advanced process control, real-time optimization. And the question is, are we still operating at the best point? That is the question which is really asked when you come to advanced process control. However, before we talk about advanced process control, we need to remind ourselves of some the objectives which were mentioned already yesterday. Some of you were not here yesterday, and you are still allowed to be here, even if you were not here yesterday. So why we control the processes? Well, to keep the plant within safe operating limits, meet environmental requirements, product specification, and operate economically. The first three, safety, environment, and product specification, are really visible. You have alarms, limits, product quality, compliance to regulations. These are usually very visible. The fourth one is really less visible, the economic objective. And this is where advanced process control and optimization can create value. This is where it that's basically its field. And where does it fit in the process control pyramid? We heard yesterday about the foundation of advanced process control. And I remind you that Umar said in one slide, I remember, for this problem, I recommend advanced process control. This is not the question I talked about, by the way. You don't need to answer right now at which point he said that. As you see, the process control pyramid, instrumentation, there is more of that in the plant, a lot of that, instrumentation, so valves and instruments, basically, valves, transmitters, analyzers, and then you go one level up, the base layer control. You heard a lot about that yesterday, the PID loops, controlling flow, pressure, level, temperature, and so on. And then you go one layer up, intermediate control. So you have the cascade loops, override control, and advanced regulatory control, where you have already multiple inputs, but one single output. This is still not advanced process control because you have one single output. A good example is the anti-surge controller, multiple inputs, but one output. One output, one actuator, one valve. So that's not based on feedback again. Even here at this level, it's based on feedback, the error. You heard that yesterday. One layer up, that is really what it is about today in this webinar, advanced process control, model predictive controller. You hear the word prediction, not feedback. Quality estimation. You need a lot of, you need much more data compared to base layer control. You remember when Omar talked about the open loop test, open loop step test. Here, you need much more data. especially when it comes to quality estimation or the so-called inferals or the soft analyzers. You take 1 month of data, something like that, and you try to make a model to predict a certain quality, multiple variables to predict a certain quality. And then one layer up, the real-time optimization. There's something important about this that one should understand. Let me take the pen. If you go from here, from the bottom up here, the computing power increases. But the other way around, down here, execution time is different. Base layer control, Omar yesterday was mentioning seconds. Advanced process control practitioners, they don't like seconds. We don't talk in seconds. They talk in minutes. So the execution is 1 minute, maybe half a minute, maybe a quarter of a minute, or more than a minute, but not seconds. We don't like the unit seconds. Over here, real-time optimization, they even talk about hours. They don't like the minutes. They talk about hours. Again, another concept which Omar mentioned yesterday. He said base layer control is not solving the problem of bad instrumentation. Yeah, of course, sluggish or it's hunting. That's not the solution for that. But I would say the same thing about advanced process control. It is not magic to solve the base layer control problems. It's not that. It needs a good foundation, a good base layer. It needs good base layer control. It needs good instrumentation. It does not take over. It needs them. It depends on them, actually. Yeah. So why do we have advanced process control when we have the BID controller? We have the base layer control. This is what Omar mentioned yesterday, to be honest. It was the distillation column. And there are loops here which interact. The reflux over here. Yes. Reflux, they will have a flow controller over here. Reflux, a pump. And the reboiler, you see steam over here. They do interact. If you increase the reflux here, it will affect temperature, pressure. The traffic in the distillation column will change. The temperature is also here in the bottom, not only on the top. They will get affected. You move the reboiler, I mean, steam, more heat. Again, the impact will not be felt here, down here. It will be felt also up there. And same for the feed flow. If it changes, the other loops will get affected. So if this stuff, APC, advanced process control, works well, the difference is really visible. You can see it. When it's on, when it's off, it's really visible. This is really a small example. Here you have two controllers, right? You have the reflux, that's a flow controller, and the reboiler steam flow, that's the second controller, and they interact. Omar said yesterday, yes, I would recommend advanced process control here. Imagine you have more controllers, which is usually the case, which interact. Because look at this bottoms product. If it's going to another column, that column will be affected by this flow. Its temperature, its the flow increment. Yeah. The difference when advanced process control is on is clearly seen for us. Advanced process control, usually you don't break the base layer control loop. You don't break the base layer loop. You have, if it's in auto, it remains in auto. I mean, you don't put it in manual. This is what I want to say. You don't break the cascade loop unless necessary. So instead of if it's a flow controller, instead of the operator giving the set point, it will be the computer, the advanced process controller, giving the set point. The operator giving a set point to the PID controller. This is what you would see. The process variable. It's not frequent, usually large moves by the human being. When advanced process control is on, it's more baby steps. It's like orchestrated steps, coordinated steps, smoother, much smoother compared to. So for an advanced process control practitioner, the moment he sees the trend, he can straight away say APC is on or APC is off. Is it the computer doing the moves or the human being? However, smoother operation is not the final objective. The real question is, how does that create value? An example from real life. On the left side, APC is not on. 5 days. You see it's all over the place because it's affected by this variable is affected by multiple variables, multiple handles. For the operator to orchestrate that, of course, a nightmare. When advanced process control is on, it will be stable, as you see. And with that, then you can exploit. Because the variability has reduced, now you can have the courage to go up here, near the limit, near the constraint. So basically, the key message is stabilization creates the room for optimization. That is the key message in advanced process control. I hope by this I answered the why. Why advanced process control? Let's go to the how. A practical question. What does or how a good APC application actually starts? It starts with people. It's not software. It doesn't start with software. It starts with people. Design workshop, APC design workshop. You see people. Really, this is the start. And I would like to ask a question to the audience. Yusuf will read later, not now. But please do answer. What do you see? There is something wrong over here. What is it? Yeah, please do write in the chat. And I expect Yusuf to note them down. And Yusuf, be aware you will be reading them out in a couple of minutes. So you see a board over here, APC Guru, control objective, he's explaining. These are the words which I used to hear in German 11 years ago. MVE, manipulated variable. Stellgröße in German. DV, Störgröße. Störgröße, disturbance. It's very interesting. In German, it's very interesting.
Okay, so
the word does disturb. Störgröße. And then the CVs, Regelgröße. And there is one more, process output variable. Prozessausgangsgröße. That's one word. Yusuf, please, any answers? What's wrong here? Go ahead.
well, as long as they don't write in German, I'll be able to read it.
Do you have any answers?
We have an answer here from Saeed Al Aamri. The flow should be reversed? Question mark. I mean control objective in the button.
Okay, control objective in the bottom. Okay.
Okay.
So Dr. Saeed Al Aamri, and who else?
He's the only one answered till now.
Okay.
Let me. Come on. We are waiting for your
Okay.
answers.
Okay,
Please
I
feel
cannot wait
free.
anymore. I'm not that much patient.
Okay.
Although because of the time, to be honest.
Yeah, yeah.
What's really wrong over here is the approach. I see the approach is really wrong. This guru, the APC guru, is behaving like the hero in the room. Yeah, I'm the APC guru. Look at me. I know the algorithm. Let me design the controller. No, Mr. APC guru, this is not the way to do it. This is really not the right way. The process engineer should explain the process. The APC engineer should sit, listen from the operator. Yeah, the operator should explain how the unit is actually operated, which handles he's moving, what is being watched, what does he watch, what does he look for, what causes him trouble, and maybe there's a controller he doesn't trust, he puts it in manual. There's a flow controller at low flow, he puts it in manual, for example. He should hear the APC engineer, he or she should hear from the process engineer explaining the operating philosophy, the economics, the constraints. If rotating equipment are involved, well, if then you have the rotating equipment engineer. He will explain about the equipment limits, sensitivities. The APC engineer should really ask the right questions. And the language being used is not DV and CV and bombard them with these terms. In fact, it's the operator language. It's the process engineer language. You're really talking about the process. You need knowledge of the process. That's why I believe most of the advanced process control practitioners have process engineering background. Unlike me, they really have, most of them, process engineering, chemical engineering, and then they need to love process control. If you have automation background, then you need to love the process, and you need to should be for you okay to hang out with process engineers. It's really multidisciplinary, and it's very important. You don't get this wrong. What's the optimization objective? Yeah, the advanced process control practitioner, his job is really to translate this later, convert this knowledge into MVs, CVs, DVs, constraints, priorities, control strategy. But that's something he does where he doesn't need these people. He should learn from them first, and then he needs data. So once the team agrees, what should be controlled, what to be optimized, in which sequence the handles should be moved, which one is what makes economical sense, basically. Then he needs data. So after this, document the outcome. What's the control objective? What's the optimization objective? The economic functions. Write the first draft of the narrative, advanced process control philosophy. Let them sign on it. Let them review it. These people here around the table, the process engineering, operation. This is very important. Let them review and approve. Once agreed, the next challenge is to collect the data, which is not so easy. Collecting data is not always a nice walk in the park. Step testing is where the plant teaches us its dynamics. There is natural tension over here. You should be mindful that you have a different objective than the operator, and there is a cost involved. Step testing the plant means you are not running, you're suboptimal. That is suboptimal operation. You are not at the optimum point, which is that is the cost by itself, which you need to calculate when you put forward, when you ask for money. This is the loss. When you step test, the plant is not at the optimum operating point. And here there are contradicting objectives. The APC guru wants movement which is big enough to produce clear response with a big or good enough signal to noise ratio. so that it can be useful, so that the data can be useful for the model he needs to build. The operator may hear this when you tell him, I would like to step the plant, I would like to disturb the plant. You're really creating disturbance. He would hear it differently. It's like you are telling him, please allow me to disturb your stable plant today. Please allow me to give you headache. Please allow me to ruin your shift day. The APC engineers needs data, but the operator responsibility is different. Yeah, he should make sure it's safe. There is stable operation. Stable is good. The APC guru says, no, excitation is good today. That is due to this reason, the method statement is very important. You write the method statement, what you will do, define the objective, preconditions. So preconditions before the step test. Usually you want it to be stable, at steady state. No excitation before the step test. What is the maximum step size we are going to do? What limits will be monitored? Alarms to be monitored. How to stop? This is very, very important. Stop criteria, because the operator might intervene and ruin the whole thing. Do other stuff because the operating point hit the alarm, for example, and you wasted your day basically. It's it's not really making a mess. It should be controlled. That's why the method statement, it is a controlled learning within the, of course, within the normal operating window, and always note down the date and time. When did you do this? This is very important for the future, even in 5 years' time, because you design an application, you have known constraints, and there are constraints you didn't think about, but that will jump in the future. Maybe one equipment, it has a temperature which was not a constraint at all, but after 5 years, it is a constraint. And if you know when there was step test, you can go back to that data from the plant historian and build the model using that data. There are different ways to perform this step test, this controlled learning. As you see here, it says sequential and concurrent. So the first one, the concurrent step testing, several variables are manipulated, are moved during, I mean, as you see, the trend almost after each other, almost at the same time. Yeah. Of course, this is more efficient. It's faster. Imagine you have 10 handles, 10 manipulated variables. This is faster, but it needs more discipline and much more planning. And stronger identification tools, because the model you have, you cannot judge by your own eyes what model is this between this MV and that CV. The second method, the sequential one, sequential step testing, you move one manipulated variable at a time. Observe the response, wait for steady state. When I say response, I mean response in that unit, not only one single variable, because advanced process control looks at the process as one single entity. It's a multi-variable problem, multiple inputs, multiple outputs. And if you like acronyms, MIMO, unlike the BID controller, single input, single output, CISO. The disadvantage here is it will take more time. In practice, the choice, whether you go with this or with that, it's not entirely up to you. Operations must be involved. Sometimes the safer and the clearer method, which everyone can understand, everyone can understand, is selected, even if it takes more time. Whether at the end of the day, whether you are testing sequential or concurrent, the APC practitioner is really trying to understand the system, the whole system, to build a map, the MV-CV map. You see on the left-hand side, the rows are the handles, manipulated variables, and the columns are the controlled variables. As you see, one manipulated variable, would affect multiple controlled variables. And what you can add to the row as well is the DV, the disturbance variable. Not every MV affects every CV. Of course, there's a structure. Understanding the structure is where process knowledge and plant data meet. The step response, well, I'll show an example of a step response, which means one MV, and then you see how that's another CV has reacted. Unlike yesterday, when we heard about the controller output, a valve, for example, and then you watch the flow, how the flow is changing. Over here, you might be moving a flow. That is your manipulated variable. And the controlled variable is, for example, quality or a temperature elsewhere. Here's an example, a real life example. You see the steps on the bottom, on the top, the red one, and the plant response, the orange color. And then you try to build a model. The good thing is for you, those who attended yesterday, Omar already mentioned this. So it's really applicable, what you learned yesterday. The second one, I find this one very interesting. From the process knowledge, one would think, you see, this is a negative gain. You reduce the handle, this MV is reducing, and at steady state, the response is increasing. Yeah, the CV is increasing, but first it goes down and then up. This one here can be estimated with two first order models. So the first one with a positive gain, as you see, going down, and the CV also goes down. So positive gain, smaller dead time. And the second one start here. The second first order transfer function will start from here. You can do two of them. It's really not about mathematical beauty. It's about the fit quality. It's recommended to try. I recommend that you already, after the first maybe two steps, you already try finding a model, because you want to know early, is my step big enough? Yeah, because imagine you spend hours up and down step testing, and then you realize my steps are not big enough for all the CVs I want to know. I don't see the response everywhere in the unit. So it's really important to start early making the fit. Don't wait till the end of the day, so that you know, yes, or at least you should observe all the anticipated controlled variables, all of them, and see that you see a good response, so that you have data which you can use to build a model. After that, you'll go to controller design, where you will design the controller. You will run simulations for all the cases, for all the scenarios. If in the design workshop you say CV1 should be within this range, it's more important. CV3 should be within another range. It's less important. You should create conflicts. You create conflicts. You start with the base case where everyone is happy, every CV is happy, and then you start creating conflicts. And it's very important that you document this. So before the simulation, you write all the scenarios, have it be reviewed, and all the expectations, what I expect as per the control and optimization objectives. And then you document what you have seen. This way people can, your peers can also help you to review. And it takes time. APC is a life cycle. Yes, there is a common mistake to think that APC is something you build, install, and then forget about. It's not like that. In reality, it is a life cycle. We already talked about the workshop. the design workshop, and yeah, base layer review, because it's not a solution for a bad base layer. It's not at all. That's why you need to fix your base layer loops first, even before step testing. And yeah, step testing we talked about. And then building the model, the control design and simulation, commissioning, of course, training the operator as well. Yeah, part of the commissioning, you need to train the operator. And yes, advanced process control practitioners do act as trainers. It's part of the handover. And then the post-implementation review. And finally, run and maintain. And you have KPIs. You monitor the uptime. You monitor that each MV, every degree of freedom you have is being used. Otherwise, why do you have a certain MV and it's not moving at all? Of course, the reason is very simple. The plant does change. Instruments do drift. Valves degrade. Heat exchangers. You have fouling, scaling. And constraints may change, as I have mentioned already, or new ones can come to the picture. Yeah. So an APC application is should be treated like a performance asset, which must be owned. Yeah? So far, it looks perfect, I believe. So why talk about RTO? Yeah, because we say advanced process control and RTO. There is actually a very known limitation when it comes to advanced process control. Being honest, there is a limitation in advanced process control. APC engineers would know that even without having process engineering background, even if you don't have process engineering background, you step test the plant at certain conditions, and then you do that same step test, but at different conditions, you will realize that the plant is not linear. So, but APC assumes that it is linear. You assume, imagine you did a step test over here, this region. So that's slope, that is your gain. Yeah, you built a model here, but another time, after maybe 2 years, you step test different conditions, and you realize, no, actually the gain between MV1 and CV1 is this one here. It is nonlinear. It's known. And this is not just theory. Let's take a practical example. This is data of a heat exchanger. So there is flow over here on the y-axis. This is the heat source, the process load, the flow to be cooled, where you want to remove heat from this one here, the y-axis, and on the x-axis is your cooling medium, basically. Years of the data points, a few years, but I removed all the and this one here is the temperature. So this temperature is affected by both, of course, at the outlet of the exchanger. Yeah, this is the temperature of the load, of the process load at the outlet of the exchanger. You would think it's linear. Look at this. Look at the hotter temperature. I want to take the Stift, the pen. So if you put the other ones, yeah, imagine you put the orange one, you will realize it's somewhere here, yeah. And down here, the orange and the black will be here near each other, which means for the same process load, yeah, for the same load, if I want to have a colder temperature, yeah, imagine 1 degree Celsius. Imagine this is 1 degree Celsius. This is how much cooling medium I need to put. But over here, it's, I think, very clear for the same load, yeah, how much cooling medium is required for the same load. So it's clear that the gain is changing. It's a known limitation in advanced process control. That's why I hope by that I'm answering why we need real-time optimization. Basically, real-time optimization, that higher layer that continuously asks, given the current plant condition, what targets should advanced process control drive? Yeah, where should it go? It's the navigation. APC is the driver. It will drive, it will solve, we say, okay, the steady state problems and or the steady state optimization and the dynamic optimization. It is the driver, but it needs the navigation. APC would move the plant dynamically, safely. RTO updates the destination all the time. Google is telling you where to head. Of course, it needs current plant data, feed, composition, information, equipment constraints, and it has the heart of it is the first principles model. So that's physics, thermodynamics. If chemical reactions are involved, chemistry as well. I mean, in that plant, it's the heart of the RTO solution. And building this model needs, of course, process knowledge, mass and energy balance, thermodynamics, equipment performance, and as I said, chemical reaction kinetics. If the plant has chemistry as well, petrochemicals. So it's not purely an automation task. You need a different skill set as well. Usually, yeah, the strongest team is process engineering when it comes to the first principle model, the chemical engineers. The model can calculate then the best operating point because it is nonlinear. The model here is nonlinear, unlike APC where we did, which is based on step testing, data which you generated from the step test. This one is based on the physics. The first principle model is based on physics and an iterative approach, which means it needs good data, because if so the solution should also take care that the first principles model, the RTO, is getting good data. Otherwise, it will not converge. The iteration, it will not reach to a solution. And because I mentioned the gains and the fact that it is nonlinear, it can also update the gains of the APC. So the APC can get two things basically. What gain I am at right now, and what is my destination? These two very important questions. So, as I said, to summarize, the discipline driver and RTO is the navigator. It does not replace APC, by the way, but it gives better targets to APC. And I'm almost done. I would like to close with three messages to summarize. Yeah, three messages. APC stabilizes the process by orchestrating, acting as the maestro of the orchestra, orchestrating these interacting variables. And then second, once variability is reduced, actually variability is distributed, I can say, because in order for the CVs to be stable, there are other variables, the MVs, which need to do more work. You have seen the difference. The operator makes less frequent moves. And then you can exploit the stability by moving closer to the constraint. For example, pushing production, hitting against a constraint, or specifications or economic targets. And then RTO, because the real plants are nonlinear and conditions do change, RTO then helps to update the target. So APC this way is not only controlling well, but controlling toward the right destination, towards the optimum. So control better and optimize smarter. Keep asking right now or today, is the target still the best target? That's the question which will be asked. That was my last slide. Thank you very much. I'll be happy to see the answer, the questions, sorry, not the answers. I've seen one answer, but now the questions. Thank you.
Thanks a lot, Engineer Khalid. We have multiple questions here, and I think you can read them one by one, since you have stopped sharing. Or do you want me to read them for you? You are muted, by the way, engineer. You might have
Okay,
muted yourself.
I am
Yeah.
scrolling. I'm scrolling down.
Okay.
Okay, the only dumb one. Okay, that's not a question. Okay, do we need to update the model? Where is it? Okay. Do we need to update the model frequently to match the physical process? Is there any way to do it automatically without human intervention? I think I did answer this. Even RTO has its limitation, you know, even RTO, because imagine a heat exchanger. With time, you'll have fouling. So that process engineer would tell you the UA has to be updated because it's not as efficient as because you have, it's like having less tubes. And there maybe AI or regression, you can call it AI for marketing purpose, can help so that you have a hybrid RTO. So RTO where certain coefficients of the first principle model get updated by AI. I hope I answered that question. No one denies the importance of APC. Some of the new oil and gas and petrochemical sites nowadays comes with APC during greenfield project. But what are the biggest challenges when implementing APC in existing operating plants? Okay. I'm not sure if these are questions which came after I finished the presentation, because to me it looks like I talked about this already. If it is green plant, I I I, I find it. I haven't done that. I don't have that experience, a green plant, but I can imagine that anyway you'll need to step test. But as a starting point, your first principles model, it will need to be a dynamic model. I mean, the steady state model is not enough. If any one of you has done that before, has seen that before, please feel free. Yusuf, should I continue reading the questions?
Yes, we have 3 more minutes to
Okay,
go.
okay, okay. Okay, as per the pyramid diagram you have shown earlier, the RTO is on the top. How does RTO interact with APC in practice? Are they always implemented together? No, they are not necessary. No, they don't need to be implemented together. Um, they, yeah, yeah, no, basically they don't need to be implemented together. First APC, and then comes the RTO, if required at all. You see, advanced process control, you will see more of it in the downstream. So the person talking should be really, I mean, you more complexities in the downstream compared to the upstream. The upstream, there is either very few ABC applications or none. Yeah. So upstream, you might find and you might not find. And then in the downstream, there is the place where you need advanced process control, and you will have also a team, RTO team even. So that is really the place. That is the field where these are more, where they make more sense. Okay. Why not implement nonlinear APC for nonlinear plants? Okay. Look, an advanced process control engineer, if he knows the variable which causes the nonlinearity, and that variable is part of his model. Imagine the nonlinearity is caused by a certain flow. That flow is part of your model. Of course, you will use it to cater for the nonlinearity. You will use it so that you have a nonlinear gain, a gain which is changing. That's given. You would use it if you know if it's so simple. There is this variable is the source of the nonlinearity. You would use that. You would do that. You would model with that nonlinearity. So I think the answer is yes. One does that, but it's not always so simple that the cause of the nonlinearity is this single variable which is part of your model. That's why you will need RTO in that case.
Khalid,
Yes,
happy
go
to
ahead,
see you. Santosh here.
Santosh.
Yeah. So excellent presentation to start with basics. Yeah. So maybe I wanted to unmute that time I could not. Greenfield project. Yeah. Just wanted to add whatever what you said. So Greenfield, yes, I mean, you can start with that, but then definitely you need to do a step test, as Khalid mentioned, to gain the main. I mean, to reach your precision. Yeah. And coming to non-linearity applications, yes, actually nowadays you have the application like paste. What you have is actually a non-linear controller. Provided you know the non-linearity between MVs and CVs, you will definitely be able to implement it. But then it comes with more time spent and more complexity when your operating region is within that uh, one region. So you better design your controller there, unless you know that you are moving uh, into the different regions, then you will definitely do that. There are tools and ways to effectively implement into the APC, the non-linearity part. Yeah.
Thank
Over
you
to
very
you,
much,
Khalid.
Santosh. It was real. Thank you, Santosh. Really happy to hear your voice. This is not
Thank
the
you.
first time I learned from you. Um, yeah, thank you.
Thank you, Nasser,
And
first
I
of
want
all,
to add,
for allowing me to join. So it was posted on LinkedIn, so I've seen it today morning and I've registered for it. Thank you.
Santosh, I would like to add one point. Let me go back to that non-linearity I have seen when I
Mhm.
said this is a heat exchanger. Usually, APC, you want to push, you want to hit against a constraint. So you would be operating most of the time in that where it is more non-linear. You are trying to
Mhm.
push against the constraint.
Mhm. Correct. So
Thank
what's
you,
your point?
Santosh. Nothing really. I just wanted to add that point.
Okay. Yeah.
And I think, engineer, let us close with this question from Anwar Al-Farsi. What factor drive the RTO to update and optimize the operating points or the gains and send new inputs to the MPC?
What factors? So I'm not sure if I understood the question correctly, but I already mentioned advanced process control. We talk about minutes. So imagine it is running every minute. The RTO solution, RTO would get the data, and it has the first principles non-linear model. Okay, and it would be running or updating at much longer time. For example, every couple of hours, 2 or 3 hours, updating gains, or more frequent, giving set point targets. So saying it is more optimal that this CV now should have this certain set point.
So Khalid, I think
So
if I
yeah,
understand the question correctly, so he's asking like what APC RTO is writing to APC. So it's basically the CV limits which RTO is trying to change based on the economics and market dynamics that you feed into the RTO, so that APC can drive the process into those new CV limits, right? I think that's what he's expecting, like what parameters RTO is writing to.
thank you. Yusuf, go ahead.
Yes, engineer. Uh, it looks like Tariq Al-Muqbali insists to know what's the software that is used to tune the plant.
Um, to tune the plant. Okay, I didn't talk about tuning when it comes to advanced process control, but yeah, maybe the question is about what software. It is software at the end of the day. and it's a server. It's not unlike the PID controller residing in the DCS, in the controller. Yeah. But I think if you just Google it and say advanced process control platforms, vendors, and then you will see the list. I don't think that I have to give a list right here.
Yeah, thank you, Engineer Khalid. This was a
Khalid,
very
sorry, Yusuf, Khalid.
yes.
Khalid, I think maybe the question is to the basics. Assalamu alaikum first. Thank you, Khalid, for the excellent presentation. There are specific software to assist in tuning the base layer controllers. Okay, if that's the question related to that, because in the beginning, when we started the research for the implementation of advanced process control, initially we could see that 80% of the gain is coming from optimizing your base layer. So you cannot go to advanced process control before you make sure that you have optimized your base layer and you have tuned it to the most optimum tooling for that at least state you want to model to build your advanced process control. If that's the case. One more thing I wanted to add to what Khalid mentioned is that when you want to drive the benefits of implementing an advanced process control, like what we have seen nowadays, that everybody is knocking your door. They want to stick an AI application to your process, thinking that with this will gonna make you gain you money and gain you extra profit. And we've seen that all of this we are dealing with the crooks, not with an actual people who understand the process. The implementation of advanced process control comes from what is the problem statement and what you want to gain. The initial things I remember from my days is that if your operator is having his hands very busy playing with the process, you know that you need to have an advanced process control. If your dead time is large and the operator need to wait for a very long time to see the response in the process, go and implement the advanced process control. If you are operating away from your constraint and you are missing economical benefits, go and implement an advanced process control. Then if you have excellent, you have tuned your advanced process control, now you go to the second step, which is RTO. And now also in the top of RTO, if you want to stick an AI model that can give you additional benefits, go and do that. Thank you, Khalid. Thank you, everybody. Santosh, great to see you around. I think you are a fan of Khalid. That's why you came over here. It was a pleasure really working with you all that time. And to everybody here, Dr. Saeed and Nasser and all the gurus on the industry, and Saadawi, Mr. Saadawi as well. Thank you very much.
My pleasure, Fahad. Assalamu alaikum, everyone. Dr. Saud, Khalid.
Thank you. Thank you all for this amazing discussion. And thank you, Engineer Khalid, for the very interesting topic. It was fruitful and we have enjoyed it. Again, everyone, if you are interested to hear more about automation, about optimization, about cybersecurity, and every other topic that is related to our fields, please go on, scan this QR code and join ISA Oman today. Tonight we have had the second session from PACO week, and tomorrow we are closing out, unfortunately, this week with our third session. Engineer Abdullah Msalhi from Petroleum Development Oman will take us through AI, predictive analytics, and smart plants. Also, we are revealing a woman guidance series next week, where we'll be hosting 3 keynote speakers, 3 high achieving women in the industry. So stay tuned and thank you. Let's call it a night. Have a good one.